Okay, so our topic, the first topic in Fluids 2, we talk about pipes in series. And again, you may or may not have covered that in the first fluids class. Most people haven't covered that, so that's our first topic. Our textbook is Fluid Mechanics by Frank White, McGraw-Hill. And you've talked about pipes and pressure drops and so on in Fluids 1. And now we extend that to two pipes. The pipes can be in series or parallel. We'll do series first and parallel later. For pipes in series, we'll look at two different configurations. This is one configuration, and the other one, let's just set this one up too, looks like this. We have two very large reservoirs. This we'll call elevation Z1, and we'll connect that to another reservoir down here, and we'll call that Z2. And we'll have maybe two pipes, and the first pipe we'll call pipe A. The flow rate is QA. The second pipe is pipe B. This should be pipe A. The second pipe is pipe B, QB. Okay, they're very similar. They're both pipes in series type problems. Let's take this guy first. We can write that from 1 to, let's call this, I'm not going to need 2 there really. We'll call that 2 to make life easy for ourselves. So let's say the right energy from 1 to 2, P1 over gamma minus P2 over gamma is equal to HF pipe A plus HF of pipe B. We neglect the difference in kinetic energy between 1 and 2. It's typically small compared to other terms. We assume it's horizontal pipe, so Z1 equals Z2. So if we want to find the pressure drop in this series piping arrangement from 1 to 2, what is equal to, divided by gamma, the head loss due to friction in pipe A plus the head loss in friction due to pipe B. And then we can go ahead and write that. We know what that is, the Darcy-Weisbach equation from Fluids 1, FL over D, V squared over 2G, and then pipe B. Okay, that's energy. We also have conservation of mass, steady state. The flow rate that goes through A must equal the flow rate that goes through B, which is VA times the area, the cross-sectional area of A, equal VB times the cross-sectional area of pipe B. So 2 equations then. We can relate this, if you want to relate this, to solve for the velocity of pipe B in terms of velocity of pipe A. So we have the diameter ratio squared. Now, in a problem like this, a couple of ways you can have this problem given to you. Number one is you can have given QA pipe, or it could be QB, the flow rate in one of the pipes. They're the same. And find the pressure drop from 1 to 2. So the second problem is given delta P, the pressure drop from 1 to 2, find Q. And of course, from the picture, Q equal QA equal QB. Let's go over here, this problem. In this particular problem, let's write energy from 1 to 2. Okay, the pressure up here is 0. Pressure at 2 on the free surface is 0 gauge. Velocity, large reservoir at 1 is 0. Velocity, large reservoir at 2 is 0. All we're left with is the difference in the elevation of these two guys, Z1 minus Z2. So we have our energy, Z1 minus Z2 is equal to, same thing. The head loss due to friction adds, the Q's are equal. Head loss due to frictions add, HF1 plus HF2. I guess I'll call that A and B, yeah, A and B. So same thing, FA L over D V squared over 2G. Okay, now we have continuity of the same thing. QA equal QB. So we have VA area of A equal VB area of B. Same conclusion. So VA is equal to the ratio of diameter squared. That's my D, that should be VB. VB, so we have dA over dB squared VA. They're very similar. In one case, you've got pressures given at 2 points, so there might be a pressure gauge at 1 and 2. And you can be given delta P, asked to find the flow rate Q. Here, you could be given the difference in the elevation of two reservoirs and asked to find Q. So again, same thing. Number 1, given my QA, same thing, QA. I know the flow rate here. Find delta Z. And number 2, given delta Z, find Q. QA or QB is all the same. The Q's are the same. Okay, so how would we do that? Let's take this simple case, given QA. So I know QA. If I know QA, I can find the velocity, okay? Q equal V times A. So if I know Q, V equal Q over A. So if I'm given QA, I can find the velocity in pipe A. And I can also find the velocity in pipe B from here. So now I know both velocities. I've got to find those F's. Typically, you're given the pipe lengths, the pipe diameters, the pipe material, okay, but you're not given F's. So I don't know the F's. I got to find FA and FB. Because I know the velocities now, because I know Q, I get the Reynolds number. I go to the Moody chart, or if you'd rather, you can go to an equation for that, but we'll look at the Moody chart. That's the way our textbook does it. And we go over here, and we know the Reynolds number, we know the pipe material and diameter, so we know the relative roughness, E over D. We go in here with the Reynolds number vertically up to the correct E over D line, horizontally across, and get F. So we find FA and FB. Once we find them, we put them in here, and we solve for delta P. Done deal. Got it. Let's go over here. If I know QA, I can find VA. Got it. If I know VA, I can find VB. Okay. I know VA and VB. I can find the Reynolds number. Rho VD over mu. I go to the Moody chart. At that Reynolds number, I go vertically up until I get to the line labeled the correct value of relative roughness. E is roughness, D is pipe diameter. I go horizontally across until I find out the F. So now I know FA and FB. I put FA and FB in this equation, and I know L's and I know D's. I solve for delta Z. Now I know delta Z. End of problem. Okay, now we do the hard one. I'm given delta P. I'm supposed to find Q. Here's the equation. I know the left-hand side now. I know the left-hand side. VA and VB, FA and FB. I don't know FA and FB because I don't know the velocities. Okay, I don't know the velocities. How many unknowns? 1, 2, 3, 4. How many equations? 1. I need more equations. Oh, here's one. I'll replace VB in that equation in terms of VA. I can do that because I know the diameters. So now I've got one equation, this one, and now VA here, VA here. Okay, what's unknown? VA, FA, and FB. Okay, 3 equations, 3 unknowns. Now I've got 1 equation. I still need 2 more equations. The Moody chart, every one of those lines labeled E over D represents an equation. This is an equation for E over D of a certain value. That's 1 equation. This is an equation for E over D. That's an equation. So I've got 2 equations here, the Moody chart. I've got this equation up here. Okay. I could solve for this. Yeah, but I have to I'm going to do it by this method. I'm going to guess those F to start with. So I guess the F values from the Moody chart. I put the F guesses in here. I calculate VA. I get VA. I can get VB since I got VA now. I can get the Reynolds number. I go back to the Moody chart with that Reynolds number and that E over D, and I check to see if my guess for F is the same as my new F I get off of here. It's an iterative problem. So anytime you don't know Q, it's going to be iterative. So this up here, since I'm given Q, non-iterative. So let's put that up there as being non-iterative. And anytime I'm not given Q, I'm going to start guessing F's. Same thing here. If I'm given Q, I can find velocities. If I can find velocities, I can find the Reynolds number. If I know the Reynolds number, I go to the Moody chart and get the F. It's not a guess. If I don't know Q, I don't know the velocity. If I don't know the velocity, I don't know the Reynolds number. If I don't know the Reynolds number, I can't get F. I've got to guess the F. This is iterative. So that's pretty much the setup of most problems that you find like this. These are series problems. But now we'll take an example and put some actual numbers in there. So let me see. I think I'm gonna take this guy right here. So I'll leave him up here, and I won't need him. Okay, so we'll put some numbers in here, and then we'll see what happens. I'm going to erase. I'll leave that on there. That's okay. So I'm going to put the numbers over here. The length, okay. What I did, I don't know why, but that's okay. I call these pipes 1 and 2 now. And I call this A and B. And I'll just redo this. Here's what I'm given, pipe 1. And you know where the roughness comes from. The roughness, epsilon or E, comes from the table in the textbook, table 6.1. And let's see, we also know delta Z, 10 meters. Find Q1, or I don't care, find Q2, the same thing. Okay, so the first thing to do is classify the problem. All right, we've got 2 reservoirs, got it. We're given what? Oh, delta Z, got it. We're asked to find what? QA, okay. Uh-oh, it's iterative. That's not the easy one. The easy one's a non-iterative problem. Okay, so we start out. We get, epsilon 1 over D1. Epsilon 2 over D2, 0.3025, 0.3020. I'm just going to go to the Moody chart now and put these guys down. Well, they're there. Okay, there should be. I think there's another 0 in there. Let me check and make sure. It's 2 zeros. Yeah, there's 3 zeros. Okay, there should be 3 zeros there. Okay, right. That's what you see on the Moody diagram in the textbook there. Okay. I want to solve for Q. Okay. I need to get V1 or V2. Okay. So I write energy A to B. So I get my delta Z is equal to F1 L1 over D1 V1 squared over 2G. They add, the friction head losses add. Got it. And then I have Q1 equal Q2. So V1 A1 equal V2 A2. And we get V1, let's write it in terms of V2. V2 equal D1 over D2 squared V1. Okay, down here, 10 equal, I don't know F1. Okay, here's a guessing game. I don't know F1. I want to make a decent guess on F1. I don't want to close my eyes and point to the Moody diagram. F1 is 0.2. No, that's the random approach. You want to make an educated guess on F1 so this thing will converge faster. So what you do is you go over there to epsilon over D point. Let's take the easy one first. Epsilon over D, 3 zeros and 2. Epsilon over D, 3 zeros and 2. There's a line on the Moody chart, label that. For my first guess, I'm going to guess I'm in the complete turbulence region, which is everything to the right of that paper. The complete turbulence region is where F is a constant with the Reynolds number. F does not change. So my best guess to start is I'm out here somewhere in complete turbulence. And most of the time you're right. So I'm out here in complete turbulence. You take a ruler or something and go to that point 0,002, take a horizontal line like this over to here, and that's going to be my first guess. And my first guess for F2 is 0.0138. F1 equal this. First guess. Got it. Relative roughness, 0.00025. 3 zeros, 25. I don't see a line here labeled 3 zeros and 25. Okay, take a pencil and sketch your own line in. I think it's right there. Okay. So now I draw this line in here. And that line is 0.00025. I interpolate between 2 and 4. I take a ruler or a piece of paper. I lay it on the Moody chart. I go across horizontally until I get my first guess for F1, 0.0142. This should be F2, pardon me. That's this guy. That's this guy. Got him. This is my first guess. There they are. Okay, put them in the energy equation. Okay, F1, 0.142. And now put in my L over D. V1 squared over 2G. Now I put in my first guess for F2, 0.138. L over D. I don't want V2 in that equation. I want V1. Okay, right here. V2 is the diameter squared, ratio squared to V1. But square velocity, that comes a fourth power now. That's the fourth power. There it is. Everything's known except V1. I know G. Solve for V1, and I get for V1 4.04 meters per second. And then I can get Q1, V1A1, .127 cubic meters per second. Okay. So, what did the problem ask for? The problem said, what is Q1? I got it. Well, no, you don't. You don't have it. Because you guessed. Because you guessed that might not be Q1. Maybe it is, maybe it's not. That's a guess. So what do I do now? Well, now I find a new Reynolds number. So I get a Reynolds number now, Reynolds number 1. Reynolds number 1, VD over nu. 4.04 velocity. Yep. Times the diameter, 0.2. Kinematic viscosity. Reynolds number is equal to 8.08 10 to the 5th. Reynolds number 2, type 2. Now, you can get the velocity from here. There's V2. I did that. When you do that, you get V2, 2.59. And D2, 0.025, 0.25, 1 times 10 to the minus 6, ambient temperature, 6.46 times 10 to the 5th. Go to Moody. Get 8.1 times 10 to the 5th. Here, I go over here. .08 10 to the 5th. I go up to the line labeled .002. That's pipe, wait, that's, oops, wrong one. That was my F1. And my epsilon over D is 2.5. So I go up to the line labeled 2.5. I read across where that is, and that F1 comes out to be 0.016. Now I go to Reynolds number 2, 6.5 times 10 to the 5th. Here. I go vertically up until I hit the line labeled .0002. I read across horizontally, and I get F2 equal .016. When you do it on the chart, you'll see they're the same. On the board, it's hard to do that way. Okay. F1 guess. No. I guess 0.142. Second time through, 0.016. Nope, that didn't converge. F2, 0.0138. I guessed. Second guess, 0.016. Oh, that didn't converge. Okay. So what I say is repeat the above calcs. Until F values converge. What that typically means then, if next time you do this, you get 0.0165 stop, you're close enough. You're within 1/1000th on the F value. Stop, because the Moody chart isn't that accurate anyway, of course, plus or minus 20%. So, how do you repeat it until they converge? Well, you take these new F guesses, 0.016. I'm not going to go through it all. You take those new F guesses, and you make this 0.016, and you make this 0.016, and you go through it now, and you get a new V1, and you get a new Q1, and you get a new Reynolds 1. And with that new Reynolds 1, you go back to the Moody chart and see if the F changed. If it didn't change, stop, you're done. If F1, F2 didn't change, stop, you're done. The iteration has converged. Okay, so that's how you do these guys, which are the tougher of the two kind of problems where you don't know Q, which means you got to guess the F to start. Okay, any questions on that? Okay, good stopping point, then we'll stop here with the pipes in series.